session. Before we start the session 1 with Professor Karmalkar, let me introduce Professor Karmalkar. Shripad Karmalkar is a professor of electrical engineering and head of the Teaching Learning Center at IIT Madras. He received the BTech and accelerated PhD degrees in electrical engineering from IIT Madras in 1983 and 1989, respectively. He has held visiting assignments at US universities, namely UC Santa Barbara, RPI, and USC. His twin interests are semiconductor devices and education. His recent devices-related research has focused on modeling and simulation of power devices, nano devices, GaN, HEMTs, and solar cells. His contributions in the field of education include video courses on solid-state devices, semiconductor device modeling, and introduction to research, hosted on the internet. He has received the Vikram Sarabhai Award for the research in 2006, IBM Faculty Award for Research and Teaching in 2007, President's nomination to the IIT Council for Contributions in Education, Science or Technology for 2019 and 22, and VLSI Society of India Best Faculty Award for Teaching, popularizing and creating some of the best minds in microelectronics in the last 30 years in India in 2021. He is an associate editor of IEEE Transactions on Education, a member of the Executive Council of AICT, and has served on several national level committees related to education and research. So welcome, Professor Karmalkar. Professor Karmalkar?
Yes.
Yeah, please welcome to the session.
Thank you so much. Yeah, for your introduction. Yeah.
So I request Professor Karmalkar to start his talk. It is over to you.
Okay. Can I get an idea of the audience? So
in the audience we have.
I will just start with some interaction with them.
Myself, yeah, sure. Please.
Okay. So I see. There are, people are still joining. So, one by one, let me find out how many of you here are faculty. Please turn on your videos. Can you turn on your videos, those who are faculty? Rupam Goswami has turned on, and Vijay Kumar, only Vijay and Rupam.
Yes,
are you two the only faculty?
I guess yeah. We have a few more faculties here. Yeah, Dr. Deepika Hazarika.
Madam, yes. You are faculty, Deepika? You are a faculty in
yes, sir. Yes, sir.
Which place?
Sir, Tezpur University, Electronics and Communication Engineering Department.
She's from the same department.
Yeah,
yes. Yeah. Tezpur. Okay. And so remaining are students, is it?
Yes, sir. Yes, students.
So, okay. So let me do it this way. All those who have a background in semiconductor devices, please turn on your videos. Let's put it like that. And it doesn't matter whether you are faculty or students. Those who have a background in semiconductor devices. So I see only 3 people turning on their videos: Rupam, Sujay, and Supriya. Supriya, you are a faculty or student?
Sir, I am an MTech student from the Department of ECE.
Okay. And Sujay?
Sir, I am a PhD scholar currently in this university under Ratul Baruah, sir.
Okay. Abhay Chaurasia?
Sir, I am a faculty of ElDeS Institute of Technology, Kanpur, Uttar Pradesh.
So you are a faculty from Indian?
ElDeS Institute of Engineering Technology, Kanpur.
Okay, good. Meenakshi Chauhan, she has raised a hand.
Yes, sir.
What is it that you want to say, Meenakshi?
Sir, actually, I am a research scholar at the LNMIT Institute, Jaipur.
Okay, but you have a background in semiconductors.
Yes, sir. Of course, I have a background in semiconductors, but the camera was not working, so I raised my hand.
Right. I understand. Yeah.
Okay,
What
sir.
about Ananya Bhattacharji? Apni
Sir,
faculty or student?
sir, I am a research scholar in Tezpur University. I am working in the field of flexible electronics under the supervision of Ratul Baruah, sir.
Okay, good. One more person had turned on the video, Mandal, I think.
Yeah. Yes. Biplab Mandal. He's a
Biplab,
faculty.
what about you? What about you? What are you?
Sir, are you there? Biplab, sir.
Yeah, I'm asking, what are you, a faculty or a student or what is it?
Is he available? Yeah.
I'm able to see Biplab.
Yeah, can you hear me, sir?
Yeah. We
Yeah,
can hear.
I'm a faculty here in Tezpur University.
You are a faculty and you have a background in semiconductors.
Yeah, yes, sir. I teach VLSI design.
Okay, thank you so much. You can all turn off your videos.
Yes, sir. Thank you, sir.
Yeah. So now those who didn't turn on their videos so far, they can turn on their videos and then I will find out a little bit about their background, because without this, we cannot proceed with the talk. I should know what background people have so that the talk can be pitched at their level. So all those who didn't turn on their videos because they didn't have a background in semiconductors. So let me see what is the background of these others. So Mrinal, what is your background?
Sir, I have a little interest in image processing, sir.
Sorry, you have an interest in?
Image processing, sir.
Image processing.
Yes.
Okay. That is fine. But student or faculty, what is it?
Sir, MTech first year, sir.
MTech student.
Yes, sir.
Okay. Fine. Akash. Yeah, you should unmute yourself.
I am also first year MTech student in Tezpur University, and I also like image processing and neural network systems.
So, but what is the topic of today? Do you know?
Yes, sir. It's mainly based on semiconductors, but yes.
Yeah. But what is the topic? Specifically, what is the topic?
Pardon, sir?
Okay. So, Mrinal, do you know what is the topic?
Semiconductor device, sir.
Yeah, but semiconductor devices is a very general term. There is a specific topic in that area. If you do not know, that's fine. Just wanted to check. Right. What about Dhruva Jyoti Hazarika? He had also turned on the videos. Dhruva Jyoti? Okay. Dhruva Jyoti, yeah. So what is your background? And do you know what is the title of the session today? Am I audible, Dhruva Jyoti? You have to unmute yourself. Okay, I think there is we are not getting across. That is fine. So there are a few who have interest in, who have a knowledge of semiconductor devices. And there are some who don't have a knowledge but have interest. Rajiv Biswas, let me check with you. Rajiv, am I audible to you? Rajiv? Okay.
He's a faculty member from Department of Physics, Tezpur University.
Acha, okay. And one more person joined. Okay, fine. Okay, so let's see. Let's get started and see how far I can pitch my talk for a general audience. Kavyashri Hazarika joined. Kavyashri, you are a faculty or a student?
Sir, I'm a PhD scholar. My area is biosensors, sir.
Biosensors. You have some background in semiconductors?
Yes, sir. Yes, sir.
Okay.
Basically, ISFET is modified into a biosensor.
Okay.
Thank you, sir.
Okay. Okay. Is my slide visible?
Yes, it's visible.
I will also just check that it is changing. What do you see on the slide? Title?
Nano and Super Junctions, Unified Perspective.
Now what do you see?
Outline.
Okay. So that means the slides are changing. Okay.
Yeah, it's working.
Now I will probably turn off my video, right?
Oh, yeah.
When I'm presenting. Right. So nano and super junctions, a unified perspective. So I will have basically 3 subtopics which will be covered here: conventional plane and planar junctions, nanoscale junction, and super junction. Now let's look at a conventional P-N junction. This is how it looks like. Okay. It has an anode contact made of metal. There is a P plus semiconductor region, and then a thin P plus semiconductor region, and then you have a thicker N-type region, whose thickness and doping is dependent on the breakdown voltage of the junction, depending on whatever is the specification. And remaining part of the silicon or semiconductor wafer is made heavily doped N-type. Okay, so that it doesn't contribute to series resistance. Why do we need this N plus? It is because you want to hold this particular P-N junction, right? Practically handle. So you can't handle this P-N junction without a thick substrate. Thickness of this N region would be varying anywhere between 3 to, it can go up to even 100 microns depending on the breakdown voltage. But even 100 microns is only 0.1 millimeter. And this region, P plus, would be fraction of a micron to about 2 or 3 microns, right? Therefore, this total thickness is very small, and you can't handle a wafer like that. As you know, many devices are made simultaneously on a wafer, right? So the wafer itself will be having a diameter of 5-inch or even 10-inch nowadays. So you can't handle a 5-inch or 10-inch diameter wafer which is 0.1 millimeter thick. Please try to imagine how much is 0.1 millimeter, right? You know how much is a millimeter and how much is 0.1 millimeter. To give you some idea, let's make a calculation. What do you think is the thickness of a paper that we normally use? In A4 size paper, what do you think is the thickness? I will give you a few seconds time. Please calculate, estimate, and then anyone who gets the answer, please tell me, what is the thickness of a paper?
Sir, 2 mm?
No, thickness of a paper, A4 size paper, thickness.
So 1 mm?
So around 0.11.
So 1 mm, evidently not, because 1 mm is fairly thick. In 1 mm, you will have several sheets of paper, right? So this is the first thing you want to understand semiconductor devices. First, we need to get an idea of the thicknesses or distance dimensions involved, right? For example, if I want to know what is the distance between Tezpur and Chennai, I need to have some idea of a kilometer. How long is a kilometer? Because we will describe this distance in terms of kilometers. Okay. So like that, we should also get an estimate of thicknesses which are very small and which are relevant to semiconductor devices. Right. So somebody said 0.1 millimeter, right? 0.1 millimeter is 100 microns. Let's assume, suppose that means there are 10 sheets of paper in 1 mm. Suppose it is, let's assume it is okay, right? Then this P plus and N together would be of the thickness of a paper, A4 size paper. Now you imagine in your paper you have cut a circular piece whose diameter is, let us say, 5-inch. Okay. And then you know how it will be, how that sheet will appear. a 5-inch circle in an A4 size paper. Evidently, that cannot be firm, right? It will be bending and so on. So that is why you need this substrate, thick substrate, to provide support. But then this thick substrate will increase the series resistance because current flow happens, let us say, in this direction, right? When the diode is forward biased. So to reduce the thickness, to reduce the series resistance of the substrate, we put a thick substrate. We increase the doping, okay, and make it N+. So that is the structure of a plane P-N junction, plane. So you can see that this junction is a plane. Now, right now in a cross section, it looks like a line, but it is a three-dimensional view, right? I mean, there is a, the plane is into the slide. Now, usually when people do work on semiconductor devices or even other structures, they restrict themselves to cross-section only. What is shown here is a cross-section. It turns out, however, that unless you have the top view and the 3D view, also apart from the cross-section, you do not have a complete idea of the device or any structure. Therefore, no one should work with the cross-section alone. One must sketch the top view also. So here is a top view of the diode. It's just a rectangle in this case. Okay, most students work with the device cross-section alone. However, they must sketch the top view and practice sketching the 3D view as well. This is very important for all those people who are working on semiconductor devices. Every device that they're using, they're working on, they must sketch top view, cross-section and 3D view. Right. Now, let me quickly tell you the story about a P-N junction like this. Historical account, how this such a P-N junction came into existence. So in 1874, today it is 1922. Okay. So I'm talking about 1874, 2022, 1922, that will be 100 years ago. And then 1874. So this means almost 150 years ago. That was a time when first rectifying contact was made, metal semiconductor contact. It was not a P-N junction, it was a metal semiconductor contact. The person was Braun. In 1907, a person by name Round came up with a light emitting diode. In 1949, the P-N junction was realized by Shockley. In 1954, these are all the developments related to a P-N junction, how it was used for multiple purposes, right? So light emitting diode, here it is a rectifying contact. And here the P-N junction, this was a metal semiconductor junction, right? So the first P-N junction was made in 1949. Then it was shown that you can use the junction as a solar cell in 1954 by Chapin, Fuller and Pearson. In 1958, a scientist by name Esaki showed that you can use this device for making oscillators, negative resistance and so on. And the device was called a tunnel diode because current mechanism through this diode was a tunneling. Okay, so that is how it was called tunnel diode. So basically if you dope both regions, P and N regions heavily, you get the tunnel diode. In 1962, Hall et al. Showed how you can make a laser out of it. In 1963, Gunn, G-U-N-N, Gunn, came up with a variation of the device and called it as transferred electron diode. In 1965, Johnston, Deloach and Cohen came up with the impact diode. These are all junctions, but variations in structure, and therefore different mechanisms of current flow are there in all this. Finally, in 1974, Chang, Esaki and Zhu proposed what is called the resonant tunneling diode. Now, that is, so what we have seen is a historical account of the devices, variety of junctions, let us say, not P-N junctions, variety of junctions. Okay. Now, let us look at the processing aspect. So far, we looked at the device and device physics, processing. So, you can look at the structure. What does it need? First, it needs a crystal. Okay, crystal, semiconductor crystal in which you can make all these things. So, 1918, Zustralski showed how you can get a crystal of semiconductor. Then in 1925, Bridgman came up with another method of growing silicon crystals or semiconductor crystals in general. Thiel and Little came up with yet another method that is called junction growth from melt in 1950. In 1952 was crystals growth by zone refining, yet another method, and this was introduced by Fan. In 1952 again, alloy junction growth. How can you do a P-N junction during growth itself? Hall and Dunlap. In again 1952, the same year, Fuller showed how you can do a diffusion. So you can see here the structure. One way is when you are growing the crystal itself, first you can dope it using N type, then you can dope it using N plus type, then N type, then P plus, like that. You can go on changing the doping when you grow the crystal out of, when you are growing the crystal itself. Instead of that, what Fuller suggested is you first have a crystal, okay, made of say N type, and then into that you diffuse P type. Instead of trying to grow all these regions, P, N, N plus regions during the crystal growth, you first have a crystal and then you diffuse from outside an impurity. And in 1957, these people, Sheftel, Kokorish, and Krasilov, they showed how you can make a chemically vapor deposited epitaxial wafer. Now, this region governs the reverse breakdown characteristics of the diode, right? Doping and thickness. So if you have to control this precisely. Now, when you are growing a large crystal, it may not be possible to control the doping very critically and also the thickness. So this particular process invention, epitaxial chemical vapor deposition, this was very important because it allowed you to grow controlled thickness of semiconductors, right? As thin as you want or as thick as you want, and also control the doping. So really, this kind of a structure that you see today was possible only after 1957. Right. Now, as against plane junction, this is a plane junction. Let us look at a planar junction, which came into being after the plane junction. So what is a planar junction? Here, the P plus region doesn't extend from left to right all through. Okay, so this P plus region is created through a window by diffusion or implantation. And therefore, its edges terminate just beyond a window. They don't extend up to this edge. You can see this difference here. So here, the junction is exposed to the surface, vertical surface. Whereas here, this vertical surface is not touching the junction. The very important achievement here. So the junction is inside and so it is secure. The problem with this particular P-N junction was that because this junction was exposed here and you can have high fields when you reverse bias the junction, therefore impurities and so on can come and stick here, right? And that will create a parallel path, leakage path, and so leakage current of this junction was very high when you reverse bias this. Now that leakage current was cut down like anything in this particular junction, which is called a planar junction. So now you can understand this better using the top view. Okay, so you create a small window in a mask. What is a mask? It is a silicon dioxide layer which doesn't allow impurities to diffuse when you are introducing impurity from the top. So in these exposed regions, here only the impurity will go into the silicon. This is all oxide and here the impurity will be blocked. That is how you can create selective regions of particular impurities. So this device is called a planar junction, AR, planar. Now here is a 3D view of this junction, how it looks. It shows that this curvature is a very critical thing from the point of view of device operation. Okay, because of the curvature, the breakdown voltage of this device will be actually less than this device where you have the plane. Why? Because from your 12th standard physics understanding, right? Your 12th standard level of understanding of physics, if you recall, it was pointed out that if you have sharp contacts, from the sharp contacts, a high field is possible, right? So same thing here, sharpness is nothing but curvature. So here fields can become high and therefore breakdown voltage reduces. Now, interestingly, the curvature is more at the corners and it is less on the sides, because here it is cylindrical and here spherical, because there are two curvatures here coming from this side as well as from this side. So really a planar junction breaks down in these regions, right, where curvature is very high. So these kind of things you cannot show unless you have the three-dimensional view. Now let's look at planar junction developments. So you can go back here and note that 1957 you had the epitaxial CVD, right? So after 1957 you could create a device like this, plane junction. So this development starts after 1957, right? In 1957, Andrus introduced what is called lithography using photoresist. So what is this lithography? So you can create patterns in a semiconductor or an insulating layer grown on semiconductor. For example, here it is silicon dioxide. You can create patterns in this like you do graphy. How can you create a pattern? So you put a mask that is nothing but a glass plate with some dark and transparent regions, and you shine light. So those dark and transparent regions will be transferred to the photoresist, which is a chemical, and then via the chemical it will be transferred to the underlying layers. So that concept was introduced by Andrus. Then Frosch and Derrick showed that you want to mask diffusion of impurities into semiconductor. You can use silicon dioxide. It's a very easily growable layer on silicon, and it will work very nicely as a mask against impurities. So you can selectively then diffuse semiconductor impurities into selected into parts of the device. Shockley in 1958 introduced ion implantation. Instead of diffusion, you can use ion implantation. So what is the difference between diffusion and ion implantation? If you want to diffuse, say, boron to create this P+ region, you have to raise the temperature of silicon here to 1000 degrees centigrade or more. Otherwise, the diffusion rate is very, very low. Okay, so this is one of the main limitations of the diffusion process. You have to do it at elevated temperatures. Also, the diffusion rate is very small. So you have to diffuse for maybe a couple of hours and so on. Now, as against this, ion implantation is a room temperature process. At room temperature itself, you can introduce the impurity. How? By applying an electric field and bombarding that on the semiconductor. So if you bombard semiconductor with phosphorus or boron atoms, or boron or phosphorus ions actually, because only ions will be accelerated by an electric field. So you accelerate using an electric field in this direction and you bombard, and then those things will go inside and create a junction like this. That is the ion implantation. That is why it's called implantation. In 1958, Kilby introduced the concept of integrated circuit, Kilby and Noyes. There were two people, okay, who came up with this. So after this developments, this planar junction became very popular. As I mentioned just now, what is the advantage, main advantage of the planar junction as compared to the plane junction? Can someone please respond to this so that I know people are engaged? What is the main advantage of this junction over this junction? Anyone?
Students, please respond to the question.
So as I mentioned, okay, structurally, what is the difference between this and this?
Sir, the junction is different. Here in the planar junction, impurities can't get attached to the side. But in the plane junction, there is a possibility of
Correct. So
Okay.
here the junction is getting exposed to the atmosphere, whereas here the junction is inside. This is the atmosphere, right? The vertical edges. So therefore the junction is secure, it is protected. And therefore the leakage current of this planar junction is very low as compared to plane junction. That is the great advantage of the planar junction. So its rectifying properties are better. Okay, now let's look at an operation of this device a little bit more. If you apply reverse bias as shown here, that is positive voltage at the bottom and negative voltage at the top, then what happens is a depletion layer is created in the end region. The shape of the depletion layer is like this. Okay, it's curved at the edges. Here it is flat, but it is curved here. Now, this curvature is what is responsible for lower breakdown voltage of this device as compared to this junction. Okay, so advantage, disadvantage both are there. Here the junction is exposed to the atmosphere, therefore leakage current is very high in reverse bias. Whereas here leakage current is very low, but breakdown voltage is also reduced, right? Because of that curvature that I mentioned here. So how can you reduce the curvature? How can I have an advantage of low leakage current? At the same time, I also get the required breakdown voltage. How can I avoid this curvature? So the way to avoid this curvature is to introduce what are called edge terminations. So here, this is a planar junction with edge termination. So what is the edge termination? You diffuse rings of P plus region like this, thin regions, surrounding this junction. Okay, so this is the top view as shown here. So you introduce P plus through this and through this. Okay. So what will happen now? The depletion layer will not curve like this here. It will go slowly, right? Like this. Gradually it will change. So curvature is reduced. The location of this ring is a very important design parameter. You must locate the ring in such a way that this curvature is minimized. So you can see that if I locate this far away, then there is no point. The ring will have no effect because the depletion region will end here. But if I locate it and merge it with this, then all that has happened is this edge has been shifted. That's all. So again, you'll get the same curvature. So for two extremes where the ring joins this P plus and the ring is far away from P plus, you're getting the same low breakdown voltage. So for some location in between, this curvature will be minimum and you'll get a high breakdown voltage. Now, let's go further. Let's start with this plane junction and look at nano and super junctions. How do you get nano and super junctions and what are the advantages? So, please see what I have done. In this N-type region, I have introduced P-type, what are called pillars or insulating pillars. So these regions here, they are either P-type semiconductor or insulator with negative interface charge. Interface charge means what? There is an interface between this insulator and this semiconductor, right? So these are lines, these are interfaces, all this. So there you have a negative charge. Okay. Suppose you create an insulator like that. Or you simply have it as an insulator with no interface charge. So you can have a structure like this. This is basically the structure of either a nano junction or a super junction. So what is the difference between nano and super? The difference has to do with the sizes involved. Okay. So let's see that. So before I see that, as I mentioned, you should also look at the top view. And the same structure, when you see from top, it will look like this. It will not only have pillars like this, lines like this, it will also have lines like this. Okay, that is something that you are not able to see here. That is why the top view is important. So what is happening is, you are ending up with N-type pillars like this in a matrix of either P-type region, all this is P-type region, or insulating region. That is how this structure will look like for nano and super. So let us look at this structure a little bit more. So the device is material in H regions is p-type semiconductor. So how do you create these regions? You etch. So what we are saying is to take this and you etch out like this, using some chemical etching, chemical process, and fill up those things with material, which is either p-type semiconductor or insulator. So if the material in H regions is p-type semiconductor, that is these regions are p-type, and pillar dimensions, that is we are talking about N pillar and insulator pillars, right? Width is 0.5 to 10 microns and height is 5 to 100 microns. Suppose the width is 1/10 of the height, you can see here. Height is 5 to 100 microns, this height. And width is this. So you always connect it to the 3D view. So here the width would be this direction as well as that direction. Then this device will be called a super junction, this structure. Okay. This was proposed by Shirota and Canada, 1978. Its theory has been developed by Fujihira in 1997. JAP journal, what does it stand for? Someone, can you tell me what is the full form of JAP?
Sir, Journal of Applied Physics.
Correct. And what is JJAP?
Sir, don't know.
What is
sir.
JJ? Anyone else? What
Japanese Journal of Applied Physics.
Correct. So Japanese Journal of Applied Physics. Okay. Then Zhong et al. Very recently also discussed various aspects of this device in 2016 in ISPSD, that is the International Workshop on Power Semiconductor Devices. Okay. And our group also very recently last year did some work on this. Now let us look at a variation of this device called the super junction. So as I said, if these regions are p-type semiconductor and the sizes are as shown here, height and width, then you call it as a super junction, right? Now a variation of this is when the material, this material, blue material, is insulator with negative interface charge. That means here you have negative charges along this interface. Height and width remain the same. You are just replacing p-type semiconductor by this. Then it is called a charge sheet super junction. Why? Because if you put this as p-type semiconductor, this entire region will be depleted in the reverse direction when the diode is reverse biased. Like the N region also will be depleted. And so you will get a negative charge from the p-type region, but it will be distributed over the width. On the other hand, here, the negative interface charge, what is the meaning of interface charge? It is not distributed all over this blue region. It is at the interface. Okay, so it's like a charge sheet, a negative charge sheet rather than a negative volume charge. Therefore, it is called a charge sheet super junction. Now let's look at a nano wire or nano film junction. The same structure, the material in H region is a insulator here. But the width and height, you can see they are very, very small. The height is 0.2 to 20 micrometer. Okay. So 20 micrometer, you want to get a idea of 20 micrometer. It is the same as thickness of the human hair. About that. That is the thickness. The height is that much thickness, this height. And the width is even smaller. Right? 0.6 microns or something. That is really 1/100th of the thickness of the human hair. That much is the width of these pillars. Then it is a nanoscale junction. And these are the people who have worked on this. Evidently, we also done some work recently. Now let's look at how do you make those nanoscale junctions. So here are examples of nanowires. How you make a nanowire. It's like sugarcane, in fact, field. It looks like that. you can see the distance. This distance is 400 nanometer. So distance between two wires is around 400. But the thickness of the wire itself, if you see, it may be a few microns, that's all. Now, how can you make junctions out of these nanowires in practice? So here are different versions of the junction. Here is one structure where you have the substrate, you have the nanowires. On the top, you make a contact using graphene. Okay. And for the contact to the bottom, so this is the back contact. So you have a top contact, graphene, and back contact. And then remaining is all insulator, right? There is polyimide. Now this top contact is actually connected here to the graphene. Another situation where you get a junction is these are nanowires, just like this. These are all verticals. Now you are making a contact to wire individually to characterize the wire. This is a platinum iridium tip, okay, that is coming and touching the wire. Now a metal semiconductor junction is created here. Now let's look at so what we are now doing is we are going to understand the physics of nanowire junctions and super junctions and show how something is common to them and what is the difference between that and the plane or the planar junction. So let us look at a plane junction. I am taking metal semiconductor as an example. So this is the metal, this is the semiconductor, and we assume that the metal depletes the semiconductor here, okay, under equilibrium. And the width of this phase charge region is W. Okay, and assume that this semiconductor is circular in top view. That is, if I see from top, it will look like a wire, right? That is why it's called a nanowire junction. So radius of the wire is R. Now, if R is very large, then this is a bulk junction. If R is small, then it is nano. So let's look at the situation when you start reducing the radius. When you reduce the radius, keeping the radius of the metal same, okay, what is going to happen is from these metal edges, field lines will come and join the semiconductor from outside. Here there was no such thing. It is not as though they are not there. Even if they are there, they are negligible because this metal is area of the metal is very large. But here, these regions become significant. So you can say you are getting what are called fringing field lines or surrounding field lines. This is called fringing field or surrounding field. Now, if you reduce the metal further, radius further, the fringing field goes on increasing. Now you can see the consequence of this fringing field. You can see that the width of the depletion region here has gone on increasing progressively. Why? Because more field lines are there terminating in this region and therefore you need to have more charge. So how can you get more charge? Because already charge per unit volume is fixed. So unless you expose or deplete more volume, you cannot get more charge. So that is why for the same condition of equilibrium, the depletion width will go on increasing when you reduce the radius. This is one of the key aspects of the physics of nanoscale junctions, that you can have space charge regions in nanoscale junctions which are really very, very long as compared to bulk junction. It depends on the thickness or radius of the wire. Now, how do you analyze this and show scientifically or using equations that this depletion width will increase? It can be shown very simply as follows. Now, those who are familiar with semiconductor devices know the Gauss Law in Z direction. Let us say this is Z direction. Gauss Law says dou E Z by dou Z is equal to rho by epsilon S. Now, can someone tell me what do these symbols mean? E, Z, rho and epsilon S? Anyone?
E is for electric field and rho is for...
Correct. Very good. Thank you. So Ez is this field. rho is this charge in this region per unit volume. This region or this region or this region, whatever, the shaded region. And epsilon s is a dielectric constant of that. Now, if it is a bulk junction, you have to use this equation. That is sufficient because all field is in one direction. But when you come here, you will have to use a three-dimensional Gauss law, because you can see the field is not just in one dimension. It is also coming like this. Here it appears to be coming from side, but you know, this is a circle. So when you see the top view, it is coming from all sides. Therefore, you have to use a three-dimensional Gauss law. And what is three-dimensional Gauss law? It contains variation with respect to radius r, in addition to variance with respect to z. So that is why you have three terms here. And right-hand side remains the same here. Directions r and z are indicated here. Same thing you can write in this form, keeping dou Ez by dou z on the left-hand side, like you have done here. So right-hand side, you can see difference between this and this is that there is some quantity which is which is subtracting from the rho by epsilon s ratio. So what follows from here? Clearly, the variation of Ez with z, the slope, will be less in this case as compared to this case, right? Because you are subtracting some quantity from here, which is same as this. So from here, if you subtract something, this quantity will reduce. Now that is shown here pictorially. That is, in this device, your Ez will vary linearly with this, because rho is a constant, because the doping is constant. So it will vary linear like this. As compared to this, in this case, your slope should reduce. So the red line here has less slope than the blue line. But since the voltage drop is same, whether it is this or this, both are under equilibrium. So there is a built-in potential. Voltage drop is same. Area under the red curve should be equal to area under the blue curve. Therefore, automatically it follows that the field is reduced because it spreads over a longer distance. Or rather, because the field is reduced or slope is reduced, it spreads over a longer distance. That is how scientifically you can show that the width here, width of this region W, or height of the depletion region, will be much increased when you reduce the radius as compared to this case. So whatever I have said, I have put it in a line. As radius reduces, dou Ez by dou z reduces. Right? Dou Ez by dou z is this. That is according to this. Resulting in decrease in Ez. You can see that Ez is decreased. And therefore, we need more W for the given potential. So if Ez is decreased, you need to extend it more. Now, using this approach, in fact, we were able to show and derive a very simple equation for an array of nanoscale junctions like this. And it is interesting to see what is that equation like. We are comparing the depletion width W of a junction like this, an array of nanoscale junctions, with the depletion width of the bulk junction, WB. That is this depletion width. And we find that the ratio is given by this formula. I'm not going to get into how this formula is derived and all that. You don't need, because it's a general audience. But it will be nice to see what is the intuition behind this. So it turns out that you can write this entire expression where what you see is there is a term called S. What is S? It is shown here. It is the separation between two wires. So it is the same as, it is rather half of separation, because this is origin 0, this is S. Okay, so 2S is the separation between wires. So this separation. And R is the radius of the wire. So R, radius of the wire. So it clearly shows if your R reduces, then this quantity will increase, showing that you will increase. On the other hand, if separation is increased, then also your depletion width is increased. reason is again clear. Separation increase, you have more fringing lines. Now, this same equation can be written very simply in this form. The same equation can be written in this form. And what do we see here? What we see here is that you get the same expression as this, which is for bulk junction, where Vd is the voltage between this metal and the semiconductor. Na is the doping of this. Q is the charge, electron charge. Epsilon is the dielectric constant. This is the formula for depletion width in a bulk junction. So formula for depletion width in a nanoscale junction, interestingly, is a similar formula to this. Please note this and this. All that has happened is this epsilon s, which is the dielectric constant of the semiconductor, has been replaced by epsilon weighted average. So this is an average dielectric constant, considering the dielectric constant of this region as well as this region. We can say it is an average dielectric constant of the medium here. And NW is an average doping, taking the doping here and here into account. So here doping is 0, and here there is a certain doping. So average. So these averages are written here. Okay. So that is a very interesting thing. The theory of the nanoscale junction. The depletion width of a nanoscale junction is has the same formula as depletion width of the bulk junction, except that the dielectric constant should be replaced by dielectric constant of the semiconductor should be replaced by average dielectric constant of this whole structure. Take into account averaging the semiconductor dielectric constant and this dielectric constant. And averaging is done like this. So what is this? Epsilon s into pi r square is the cross-sectional area of the wire, plus epsilon A is the dielectric constant of this remaining region, insulator, into area of this region, which is like a ring. So s square minus r square into pi, and divided by total area, pi s square. That is how you get the average dielectric constant. Same approach you adopt for doping. Instead of epsilon s, you put Na here. And instead of epsilon A, you are putting 0 because the insulator doesn't have any doping. So the conclusion is, in array of nanowires, the width W is given by the bulk expression with dielectric constant epsilon and doping N replaced by their weighted averages over cross sections of the wire and the ambient. Okay. Now I'll pause here and see if people have any questions. Anybody has any question?
Yes, anybody from the audience?
Yeah. So I have about 10 more minutes. Now I will show you how you analyze the super junction also in a somewhat similar fashion. So let me go to the super junction. I will skip this. Let me go to the super junction. Now, how do you get the super junction? You start with a conventional junction like this. You have metal and some region thicknesses and doping has been shown, corresponding to a rating of 700 kilovolts. So 12 micron thickness here and 7 in 10 power 16 doping. This corresponds to this. Now I'm not going to tell you how you get these numbers. It's not required also. Okay. I'm just giving you some feel, taking a practical structure to show you what is the difference between a conventional junction and a super junction. Now, if I etch regions in this, as shown here, and then in this etch regions, I create a structure like this. So what I do is I etch the region and I diffuse or implant p-type along the wall like this, and I fill up the remaining part with an insulator. The size of this is same as this. As far as this width of this pillars and so on is concerned, the sizes are shown here. So how do you do that? You etch. Then you implant p-type region, and then you put silicon dioxide, fill it up with silicon dioxide. And after that, you deposit a metal on the top. Then you get the super junction. So let us see what advantage do you get what advantage this structure has over a structure like this. To understand that, let us assume both are reverse biased. It turns out that this device will break down at 1.35 kilovolt. That is almost double the breakdown voltage of this 0.7 kilovolts. Let's explain why. So you are getting increase in breakdown voltage. How? You will give a simple explanation. So here the field is always one dimensional because the junction is plane, Schottky junction, metal semiconductor junction is plane. The field is always perpendicular to this junction or junction plane. Here, however, you have a metal semiconductor junction like this, which creates this EY. In addition, you have this P-N junction, vertical P-N junction, which will create a lateral field like this, which will be, the charge will be positive in N-type and negative in P-type. That is why it is directed from N to P. So this is a two-dimensional field distribution. And based on this, you can show why the breakdown voltage will reduce. If you recall, we had told here how the two-dimensional nature here reduces the field. If in bulk, the field distribution is like this, in this nanowire, it is flatter, right? So field is reduced. Same idea is being used here. If it is two-dimensional, the field will be reduced. So your equation for Gauss law will be like this in this situation. Dou Ey by dou y is Q&D by epsilon minus dou Ex by dou x. Like this. And therefore, the slope is reduced. Dou Ey by dou y is reduced as compared to the one time here, this situation, where it is Q&D by epsilon. So this is shown using the field picture. For the conventional junction, field picture is like this. I am going in this direction. Please note. This Y is, I have shown here, Y is downward from the top. X is rightward. So when I go downward, I take a cross section here, my field will be like this, reduced. On the other hand, if I take the same cross section here, then what will be the field picture? It is shown here. The AA prime cross section is vertical cross section and BB prime is along this particular junction. Okay, that is a small difference between AA prime and BB prime. Don't bother about it. So basically what you say is the field is much more flat and it is reduced as compared to this. And that is the reason for increase in the breakdown voltage. You can see that breakdown voltage is nothing but area under the field picture. So this area is much less than the area under either the red or the green curve because the field is more flat. So this is how in super junctions you can increase the breakdown voltage. And both the super junction and the nanoscale junction are analyzed using two-dimensional or three-dimensional Gauss law. Okay, so something common to both of them. In both cases, fields are reduced because of the two-dimensional nature of the field distribution. Yes, I think with that, I will close because these other things will be understood only by people who are more advanced. So I will come to the end. Summarize. So what have we done? So what we have done is we have discussed several important points. We showed how a plane junction evolved historically, plane P-N junction. So history goes back to 150 years. Okay, when the junction evolved from those days. Then the process for making a junction, how it has evolved, how the various steps like crystal growth, epitaxial crystal growth, then diffusion, implantation, lithography, and so on, how these have evolved in early part of or middle part of 20th century. Then we showed how the same simple P-N junction, you can create pillars of opposite polarity of semiconductor or insulators, and you can, depending on the size, if it is a big junction trying to manage kilovolt or more breakdown voltage and several tens or hundreds of amperes of current, then it is a super junction. It is called a super junction. On the other hand, if it is a small junction with nanoscale dimensions, right, this structure, then it is called a nanoscale junction. And we have discussed how the fields are reduced in nanoscale junction as well because of the two-dimensional nature. And both the super junction and nanoscale junction can be analyzed using two-dimensional Gauss law in reverse bias. Okay, so I think with that I will close my talk. If any questions, I'll be happy to take.
Yeah,
let me make myself visible.
Yeah, the talk was really informative. I guess our MTech students and research scholars must have been benefited from the talk. So it's a time for questions. All the listeners, any questions? Dr. Goswami, just check that if we have any questions from the YouTube streaming.
YouTube also. So
okay.
all the participants
They have joined online.
So what we can do is we can probably call a couple of people and see. So Kavyashri, did you understand the talk, Kavyashri?
Good evening, sir. It was a wonderful talk. I have a question. I was actually commenting on the chat box. So how do we control the mobility when we increase the doping? Like in the first case, the conventional block diagram which you showed, you said that we increase the doping. Yeah, in the middle. Yes, sir, absolutely true. So in the middle layer, second layer, third layer, sorry, we increase the doping to a larger extent. And the final layer also we increase, we do we increase it more. So when we increase the doping, definitely there will be some hindrance to the path of journey of the charge. So how do we control that? Like the scattering and everything.
No. You are saying in this region, how do you control mobility?
Yes.
So I see the mobility is a function of doping.
Yes.
And it is also a function of defect level in the impurities, in the crystal. So you have to grow a very pure crystal to get a high mobility.
Okay.
Okay. But even after you do that, if your doping is high, your mobility will reduce. If your doping is low, mobility will be more. Right? But then doping is governed by breakdown voltage. You want high breakdown voltage, you can have less doping, will be higher, but then you will lose on the mobility.
Yes, sir. So how is that analyzed, sir? Finally, if we need a crystal, like if we need a device to be appropriate. So
I know. What you're saying is that how do you design this to meet a certain specification?
Yes, sir, absolutely.
Yeah, so that is what I said. So what you will do is you will first take the breakdown voltage, and based on the breakdown voltage, there is a formula which will tell you how much should be your width, or rather height or thickness of this layer, and how much should be the doping.
Okay.
Right? Then now you analyze once you have fixed the doping here. See, this will be heavy, so these are not really there's no need to control this very much. Really, this is the region which should be controlled. So based on that, now you consider the device under forward bias.
Okay.
And you find out what will be the current density for a given voltage.
Okay.
And then, depending on how much current you want, you choose your area.
Okay.
So that is the way it is designed.
Okay.
So automatically, if your mobility is low, you will get a lower current for a given voltage. You will have to use a higher area to get the same current.
Okay.
Yeah.
Okay. Thank you, sir. Thank you so much.
So one question we have from one participant attending on YouTube. So he's asking that how we can reduce the thickness of a junction to a nano level, which parameter we have to optimize during this junction formation, so that the junction is formed without any unwanted impurity.
So the process, how do you? So you can see here. That is why I showed this. He's basically asking how do you create such nanowire? That is it amounts to saying that.
Yes.
Okay. So there is a process. So what you have to do is you have to take a substrate. You have to create small islands like this, thin circular things, right? Like dots on a substrate, or women will understand it better by you have that paper on which you have small bindis, right? When you buy the bindis, that is how they look like. There is a cardboard, and on that you have the small circles dotted like that. So exactly that is how the substrate will be. And then using a chemical reaction, you on those dots or bindis, you grow silicon. It's same as chemical vapor deposition. Only in those areas the silicon will grow. That is how you create these wires. So size of the wire you can control by controlling size of the bindis which you deposit, right? And then height of the wire you control by rate of the reaction, temperature, which is controlled in turn by rate of the reaction. Rate of the reaction, which is controlled by the temperature of the reaction, and so on. So that is how you can decide the height and duration. So temperature and duration of the reaction will decide the height. That is how you can control the height and doping of this, which will then be used, right, to make these diodes like this.
Okay.
Or like this here is shown, and there will be a top contact to all of this. I hope that will give some simple answer to your question.
All right. So I hope Jitendra Kumar has got his answer. Okay. So any more questions from the audience? Please.
Sir?
Yeah, Ananya.
Sir, Manu sir, continue, sir.
I just wanted to know, sir, what is the role of the graphene that has been deposited?
Oh, no, that is in this particular structure. This is only acting like a contact. How do you deposit a contact? No. So here, graphene is the contact.
So can any other metal serve the same purpose, or?
Yeah. So you can have different. You can even put nickel or something. Any other metal also can be put to connect all these things from the top, right?
Yeah.
Here, let me see if I have another diagram. No. Yeah. Here you can see here. For example, here you can see titanium.
Okay.
And gold. Of course, this is only one element I have shown, but basically it is an array. This is one wire I have shown, and then actually there are multiple wires like this. So you can see here the top contact here, right? This one metal.
Yes, sir.
Okay, Ananya, you can ask a question.
Sir, in the structure, you have used the polyimide in the surrounding sides.
Sorry, I think your voice broke, Ananya. Can you please repeat?
Sir, am I audible?
Yeah.
Sir, in the structure in that nanowire array, sir, you have surrounded that structure with polyimide in that structure.
Yeah, that is an insulator basically.
Okay, so the entire one is surrounded by polyimide or only the side ones?
Yeah. No. Not just the sides.
Okay, and sir, in the equation, the cylindrical coordinate system has been used, right, for the equation? Yeah. Okay. So, sir, actually, I had that doubt there that how that ER by R came. So now I got it. Thank you, sir.
Okay, any more from the audience?
So finally, I want to tell, because there are a large number of students here, whenever you are analyzing a device, you please remember what I told right in the beginning. And that is this one. Most students work with a device cross-section alone. They must sketch the top view and practice 3D view also. And I've given you examples of what will you miss if you don't consider the 3D view and top view, right? You won't be able to talk about this kind of curvatures and this kind of curvature, which is different in the corners and in the edges. So all these kind of details you will miss. So every device, you must sketch cross-section, top view and 3D view. I have seen students doing a PhD on particular device in which they will only show cross-section. And they only when questions are asked, they realize, oh, they should have known the top view also. So here also I have shown you how the top view adds a lot of understanding, right, about the entire structure. Similarly, here also. If I didn't show the top view, you will not understand how the structure is in 3 dimensions. Okay, so that is one point I wanted to tell, which all students can carry with them.
It's a crucial point. So I think there is no more. Irfan. Would you like to ask some question, Irfan?
No, sir. No, sir.
Okay. Okay. So I hope there is no more immediate questions from the audience. Thank you, sir, for this wonderful talk and your time. And thank you for joining us.
Yeah, thank you so much. I hope they got something out of this.
Definitely. Dr. Goswami.
Yes, sir.
Yeah, please, over to you.
Yeah, thank you, sir. And thank you, Professor Karmalkar, for this wonderful talk on junctions, nano and super junctions. And I'm pretty interested in the equations that you have shown. I'll go through the work, and then if I have any doubt, I'll contact you for sure. Yeah. Thank you, sir. Thank you so much.
Thank you. Thank you for joining us.
Okay. Thank you. I can leave the meeting.
Yes, sir. Yes. Over to you, sir.
Yeah. So, Dr. Hudait have joined?
Yes. I think so.
I cannot see his name here.
Professor Mantu Hudait. Okay, I'll WhatsApp call. I'm doing the WhatsApp call. He'll join soon. Okay. Vijay.
You just give him a message. Yes.
I'm calling him.
Yes.
I'm calling him. WhatsApp call.
I think he had joined.
Yeah, actually he has. Yeah.
Professor Hudait, are you there online? Professor Hudait?
Oh, he's typing me. He's typing me. Dr. Mantu Hudait, you just joined. You just joined. He's sharing screen just now. Vijay.
He had joined.
He's joining. He's joining.
Okay, hello. Maybe this one.
Yes, you join it. Has to join it. It's coming. Yes.
Okay, 1 second. Can you?
No, yes. Yes. Screen is coming.
Yes, we can see your screen.
Okay.
Can you see? Sorry. Can you see my title?
Everything we are seeing.
Yeah.
Visible. All are visible.
Your slides are.
Okay, sorry. Thank you.
Thank you.
Okay. Let me see my camera. Okay. This camera has to work, otherwise cannot be present. Okay.
Professor Hudait,
Go back to Vijay. Go back to Vijay. Okay, we just call to the.
Professor Hudait, am I audible?
Professor Hudait.
Professor Hudait?
Vijay, he's joining because he has given the screen share. Now he'll be joining now.
Maybe that voice we were listening from your microphone, I think.
My microphone we are listening.
Yes.
Yes, sir. Yes, sir. Actually, we are listening from Sahu sir's microphone.
But how he's presenting his slides?
Actually, he's presenting in.
So what is that? He has to make it on. Screen share. Let me call him. Let me call.
Because he's able to share his slides, but his voice is not audible.
Yes, sir. So it's showing some companion mode or something. So I think it's due to that. Google Meet companion mode.
Okay.
Sir, microphone is to be off, sir. So that's why he's not audible.
Whose microphone?
Sir. Oh, that's sir.
Okay.
Vijay?
Yes.
He's not able to connect you.
Maybe he again logged off.
Let me call.
What happening here?
Tell me.
Yeah, what happening? So I'm just exit from the Google Meet. I'm entering right now. I have no clue on it. Okay, I'm just figuring out now.
Okay.
Give me. Okay, 1 second here. He said that. Okay, join now. I did that. Okay.
Now he had joined.
Now it is coming.
Professor Hudait, you please unmute yourself.
Now you share the screen. Okay. I'm just. Hello, Mantu.
Yes. I'm just making. Sorry. Where the shared screen? Do you know?
Yes.
No. That's the raised hand. Present now. It's present now. Yes.
Yes.
Yes, sir.
Okay. Let me check here. Share your enter screen. Okay. And allow. Select window screen. Should be screen 1? No. Not that, right? Is it? Okay, hello. Let's see here. Can you see my screen? Yes?
Not yet.
Not yet. Okay. Here, there should be a somewhere called share your screen. Where is that?
Yes, sir. We are able to see your screen.
You are able to see my screen?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Okay. What happened? Somewhere. Okay. I'm controlling or somebody controlling. Let me say. Okay. So now see my presentation. Yes, no?
Yes, it's
Yes.
coming.
Yes. Yes, it is clear.
Okay. Perfect.
Now it is make it full screen.
Okay, make it full screen. Yes. Now can you see?
Yeah. Good.
Yes,
Okay.
yes.
Excellent.
Okay.
Good job.
Okay, sorry. So, do you want me to start?
Before you start, Professor Hudait, let me introduce you to the listeners.
Okay, sure. No rush. Go ahead.
Okay. Welcome, Professor Hudait, to this session. So for the audience, I would like to tell them that Professor Hudait will be talking on extremely low power logic and photonics, challenges and opportunities. So about Dr. Hudait, he's an associate professor in the Bradley Department of Electrical and Computer Engineering, Virginia Tech. And prior joining to Virginia Tech, he was a senior engineer in the Intel Corporation's Advanced Transistor and Nanotechnology Group. His low power transistor research was press released in 2007 and 2009 and received 2 divisional recognition awards from Intel, 60 issued US patents, and over 185 technical publications. His research at Virginia Tech focuses on next generation materials and devices, tunable laser, and long wavelength photodetectors. Dr. Hudait's teaching focuses on integrating research and industry experience into the curriculum. He's a senior member of the IEEE and AVS member. So with this, I'll request Professor Hudait to start his talk. Please, over to you.
Okay, first of all, thank you for Rupam and Professor Partho and others inviting us to show some of our research that we are working here at Virginia Tech. And that mostly the work that I'm going to present here, I removed the circuit aspect of it that some of my students did the work. This entire presentation are mostly the materials. How do you do the interface engineering and how do you do it? Is it blue sky? Can you do it? Can you make it? So that's the kind of stuff that I'm going to present here. And that materials and device concept that or photonics that leads to low power logic, and then people are talking about photonics. As you all know, that transistor was invented in 1947, and if you Google it up, and you know that material they use germanium, 1947. But all our microprocessors still today based on silicon. But what happened? That germanium completely you call dead, or people are bringing back with the tin, with the other material. I'm going to show you the challenges that materials that people are facing it. And sometimes people publish paper, they never talk about it. They never tell you that, and they showcase some material. They have no clue on it if you want to synthesize in your lab. So my students, I didn't mention my name, my students, without my students' help, this work I cannot present here. And there are a lot of collaborator work as well that we do a lot of analysis outside our department. So then I will give you some introduction, and mostly I will present our work. And please stop me anywhere, any questions you have, type me, follow up, anything you like. And mostly I'm going to talk about the material that you use for logic and strain germanium quantum laser. So people are talking about the laser. And there are lots of work has been done germanium on silicon directly deposited. People are going to make a laser. Yes, you can, but the threshold voltage of the laser is 3000 kilo ohm per centimeter square. So that is no good. So people are talking about how can I have a low threshold current laser. So I'm going to show you that we are working on it. And step by step, I can walk through you that and how difficult or how easy it is. Then I'm going to show you some facilities and then challenges summary. Maybe we can work together, some aspect of it. I can tell you that what you don't understand. Maybe someone can collaborate, we can collaborate on that. So let's see the why do you need now. So this is my student show me that, and mobile devices that we all need. I'm going to just show you that. And the data center, right? Data center, all our data, we call cloud. Sometimes the student, we ask, do you know mean the cloud? Like a fifth grader, when you teach them, they said cloud means the cloud on the sky. I said, no. All your information is stored somewhere else. Look at the data center here. So that means that all the processor today built in here, the data center using the silicon microprocessor. The question is that can you able to do something that power consumption that data center are facing it. Now, if people talk about called IoT or Internet of Things, like so many devices, I'll give you a honest opinion. When we came here, United States 2000, we had one cell phone, just one. Today, in our house, my wife, my two daughters, and me, we might have a 20 or 30 devices. It means we have a camera built in, weight watcher where you make your weight, that weight gives you your phone. You can track your watch, your exercise watch. There's so many devices that are connected. Everybody needs a power to turn on. And it is so scared that if you see, look at that here, the 2020, we are already crossed 50 billion devices connected. And how many zettabyte annual traffic data? 2 zettabyte annual traffic data. Look at that. This is the data came from Cisco presented here. And look at the devices. In fact, you see, let me see, there's a pointer. Was he looking at pointer here? Is it pointer? Yeah. So you see that here, the door knob, we have that. You come to our house, you have an iPhone, we give you a command and your iPhone or your Android phone open the door, our house, then you can enter in, then it automatically lock. So you see the connected devices, and every device need a power to turn on. Now look at how scary part of it. They say the Semiconductor Association, they presented that world energy can produce, the energy they can produce, how much here? And how much we need to use a benchmark here. Look at that here. That junction, this is so scared that the energy that we can produce, hold up, I couldn't, I'll just stop, sorry. The laser pointer, okay. Anyone knows the laser pointer, how to stop it? It
So
does not allow me to.
you can click on escape once.
Okay,
Escape.
I did that. Okay. No.
No. Okay.
Okay. So wait. Didn't
Or you
allow
can
me
try
to move my mouse.
right
Sorry.
clicking on it. Right clicking.
I did that. It does not do anything.
Oh.
Gosh. My keyboard is working. It doesn't. Does the pointer doesn't allow to move or? Oh, this is so annoying, right? So.
No, it's okay, sir. It's okay.
Okay. Okay. I think. Okay. Now I know. Okay. I think I have to. Sorry, doing something. So let me see if I can move my slide here. Okay. I'm really sorry. This is what happened. We use Zoom, not the Meet. So, okay. So let me.
Yeah, it's okay, sir. It's fine. It's fine. No issues, sir.
Okay. We're just. Okay. Let me. Now you said escape. Why couldn't allow me to? Okay. Okay. Thank you. Thank you. Okay. Okay, so back to the future. My goodness, this is okay. Here, perfect. Let me see here. Okay, I won't use the pointer, so that way it won't stop. So you see that here the energy production is so much that you can do, and the connected devices. So we need to do something on that, the energy efficient. You will be thinking that, does it mean that our silicon microprocessor iPhone 13 has 13 billion transistor not energy efficient? It is energy efficient. Question is that we are not talking about that. You are talking about the data center. How can you do a optical interconnect? So the solution is, can you have something that energy efficient low power device, some sort of device, not the MOSFET, that can lead to this energy reduction for the devices you are using. We do not need a high speed, but we need lots of devices. So you see, this is a slide came from Intel. I'm the ex-Intel guy. They're talking about all the copper to optical interconnect. And if you follow up this nice slide present them many times, but none of them has been implemented so far. Means they have not done those optical interconnects till today on their silicon microprocessor. That you are thinking that how difficult that is. Yes, I can show you that how difficult the material that when you want to interconnect. You cannot have a optical interconnect of silicon, because we all know that silicon is an indirect band gap, and indirect band gap does not emit light. So we need some sort of light source that can be integrated on a silicon platform. So who would be the case? Is it a germanium? We'll show you some data there. And this, again, the same slide, they are talking about future monolithic. You see that CMOS circuitry and CMOS circuitry here and on the right-hand side, and then filter and modulator and all sort of stuff. People are talking about that, can you make a future monolithic integrated circuits, right? So now, the recent paper is a very interesting paper. I will ask student to read it. It is a really cool paper. It is a Berkeley, IBM, and then what they did, can tell you that they have a chip on your left and memory processor unit and memory on your right. Please remember that all the copper interconnect memory to processor. So what they did, they used an external laser 1.18 micron. It's close to red color, near infrared, consider. They use the laser to interconnect between the processor and the memory. They built that, but not the billion transistor. Then they did a processing unit, and so the teapot, you see that here in the picture, that basically they generated by programming that the light can talk between the chip and the processor unit. This is not heterogeneous. This is external light source, laser source, and then they connect that. And they're talking about that, can you able to make a heterogeneous laser on silicon? Maybe the first step that demonstrated. That's what the paper came in the Nature. So no heterogeneous, it is just external source. So now if you see follow up on that, there are every country bringing a heterogeneous picture. Can you believe, see that here? Laser detector, fiber optics filter, modulator. So I asked my student that, can you come up, you guys, to do something picture like that? He said, why do you need it? They have already. I said, no, just have our own. So then this is, this, if you read this is so nice looking picture, but can you able to build it? Can you build one device? Just one, forget about it. Silicon photonics, can you do on your microprocessor? Because how difficult, you'll see that. So then my student came up this picture. Okay, if you ask me, probably I'll fail on that. And that basically they're going to put everything on one silicon platform. So I'll walk through that. Silicon, the whole idea was to have a processor that can have a laser that can interconnect, and they have a microprocessor unit. Please remember, we are not going to build silicon microprocessor in our group because we cannot make a 3 nanometer transistor. So we want to make a alternate to silicon material, that microprocessor. I'm going to show you some data that my student left Bangalore Intel, and he came here. He's IIT Delhi dude and went to Intel India, came to our group, and he just produced some data. So interesting. I'm going to show you the data that I put it for you. So these are the students that on the top, Michael Subhadev, that row, these are the new students, and half of the students, maybe more than half of the students, they are Intel. Because I'm an Intel guy, as soon as they see that this student did some interesting work, then they basically like they absorb them. We call Amazon drops it. Basically, Virginia Tech just drops students to the just intern. They go there and work. So Peter, Patrick, these are all the kids that all are intern. They're all building transistor. So you all know genius that 1959 said this presentation that new materials, you need that. Even though the Moore's law or whatever it is, the new materials and that we will come up every day, the 2D materials or semiconductor materials or graphene or nanotube or anything, all new material that need for different purpose, different devices, device concept. Basically, I should say new materials we need for our daily life that make those devices for us. So with that, I'm going to show you, I hope I'll show you some brief. Then I'm going to show you that dissect two problem. Going to just talk about our group, tunnel FET and FinFET. Not device, is a material concept on it. So my student put together a slide for me, and he said that, please check here, that you see that there is a fire on that. Your laptop, if you go back, your laptop, maybe, I should say 6 years back, if you have your mom and dad or somebody has it or friend has it, or you had it, you know, the laptop, the fan they built underneath the computer, basically the heat dissipates bottom. Now they realize that I have a computer that I burn it because I work on the bed and it is burned because the heat cannot dissipate. The fan is connected underneath the computer. So that why does it mean? That means that the computer, each processor or each transistor, they operate around 1.2 volt when you teach the class. But current FinFET transistor on the right hand side, you see that I put a picture from 10 nanometer Intel 3rd generation transistor. I don't have it. At least the 14 nanometer I have, those transistors around operate about 0.7 volt, 0.66, 0.7 volt versus 1.2 volt. That means that your active power in the middle graph, which is the computer or processor is working, and sub-threshold power where it is off, you can consider that. And you see that when the computer is not working, is leaking the power. Means if I leave my computer for 15 days, the battery basically discharge is dead. So none of the things will work. So basically that we need to make something energy efficient. So what can be the case? Should we do power consumption when we teach? We have a tri-gate on the left-hand side, linear saturation on the transistor class, we teach that. But if you see that the P power dissipation, dynamic power dissipation when you teach, means when the transistor is on, N is the number of transistor. Think about it, Apple iPhone or your Android phone or your, OnePlus phone, you have like a 11 billion transistor. That's the number, 11 billion transistor. See the capacitor that you have that charging and discharging, and VDD, the voltage, F is the frequency, how fast or how many times you turn on, turn off. Think about that. And you see that the leakage power, the dynamic power dissipates, and I off when it is off state, and VDD and IC, which is ISC, which is the both are saturation, right? In the class we teach. So that means the bottom line is that how do you reduce that P power that? So obviously, N can you reduce? So if you ask our kid or our friends or mom or dad or wife that, hey, do you need a computer where there is only 100 million? My little kid, even little one, she said that, Dad, this is too slow. I push the button, I couldn't do my TikTok and I couldn't do anything. I don't want, give me your laptop. So she wants a computer which is built in billions of transistors. That means the power consumption is one of the very, very important part. So now, but on current, in the class we teach on current is the most important. On current, like our salary, how much money do we make? How much salary did I get? It's like on current in a transistor. What is the transistor giving you the current? That's the most important part in one of the benchmarking parameter. That must be high. How can I make it high? If I make it VDD minus VTH, that's square. If I reduce that, for example, 0.6 square versus 1 square, my ion current has really decreased. So I cannot have that. So needs to be scaled together. So with that, what kind of devices we all know that I'm going to just briefly to show you that you need an ideal transistor, which is the orange color. Can you have that? Almost a zero voltage 0.1 volt. Intel asked us, can you give us a transistor can operate 0.2 volt? And they have an announcement call already, 0.2 volt, less than 0.2 volt transistor. Imagine that i7 processor, it junction temperature is about 100 degrees C. If you calculate KT values, you figure it out what should be the thermal energy when we are using the computer right now. So we need to have something that shaft threshold slope, and we all think that we need a very steep shaft threshold slope. That means at very low voltage we can turn on. So tunnel FET, people all talk about it, and lots of work people have done, but nowhere this FET goes because it's pretty much dead piece. I can tell you the why it is be the case. And this is very interesting materials work. We all work on it, but it's extremely difficult to make it a billions of transistors on that. So give you a student, is the student there, very brief to you that MOSFET, it doesn't tunnel on the top, the red color, the crossing point, and they go over to the barrier, the carrier, the black dot, and the tunnel FET, it is carrier need to tunnel. Is the green color on, wherever the on green color, you see that the carrier need to tunnel the valence band to the conduction band. And please check on the top in MOSFET, your source and drain both are symmetric. Both are symmetric means the source I can make it drain, I can make it source. What I need to do, I need to connect the proper voltage terminal. But the tunnel FET is asymmetric device, means if you have N FET, your P has to be the source. If you P FET, your N plus has to be the source. Please watch that. You cannot make a memory device or anything using the tunnel FET. You need another tunnel FET where switching is upward or downward. You need a two transistor goes together because those are asymmetric. So then this is the we all know that, and then this is the good thing. Okay, basically then we see the last one, middle one. What we are going to show that the material, now coming back to the all material challenge, that you see the EV effective, that S is the source, C is the channel, and channel is the in gas, and I don't take a risk on the laser pointer. Below the S, which is the valence band, above the C, which is the box, where the gallium arsenide and antimony written there, that's your conduction band. Think about it. Your carrier need to go from valence band of the source, go to conduction band on your channel. So that's the staggered part. That's the EV effective. How small can you make? That's your lambda. That's your lambda on the tunneling probability, WKB approximation tunnel probability. I don't want to go tell you the math or the details. The lambda is the important part. How lambda can you make? So then the right side, that zero tunneling, that means the carrier can easily tunnel, but they can come back too. It's like your neighbor in your house have a barrier. You can go, your neighbor can come in, right? There is no barrier, no boundaries there. That means the op current is so large on the right-hand side device, which is a broken gap. So you cannot have a broken gap. You need to have a staggered gap. So why not a homojunction? Because the lambda is too large. You want the lambda should be very small so the carrier can tunnel. Now look, that basically to give you the material stack of gallium arsenide antimonide, and where the EV effective, that EV effective has to be small. What Intel want? Intel want 0.1. 0.1 to make it. Why with this material system can make you lattice matching. Means if you have a defects between the interface of gallium arsenide, antimonide and InGas, we call the game is over. Means it's done, it's dead. So that EV effective has to be very small and has to be lattice match, has to be defect free, has to be active defect free. Means there are maybe defects, but when you make a turn on the transistor, there is nothing current coming out. It's all an off state current. It's like a registered behavior. So, and that basically the design, I'm not going to go through that. I'm going to show you that. Then what do we need that? This is the presentation done by Intel. And that person, which is a young committee member, and these guys became super famous by designing this. Okay. So you see that target, please watch that, the target. What is it? Gallium antimonide / indium arsenide. If you can see my slide there and see the green color, happy face. Okay, come back here for a minute. Please check that here. Gallium antimonide, indium arsenide. What is that? That's broken gap. That broken gap, yes, it will give you on current. Yes, we agreed that. But what happened the off current? There's no question answered. So I say that what happened the off current? Did you fabricate the device? You have billions of dollars. You have no big deal to fabricate it. If I'm a materials guy, if you want to ask me to fabricate and give you a very low off-state current, I don't think I'm there to sign off. Because that is the off current, because that is a broken band gap. It's like an open kind of stuff that carrier moving it. So the question is, what do you need then? That's the case. And before you do that, okay. So just to give you because this is the talk, and give you just like a two honest opinion. You see the gallium arsenide, antimonide, and InGaAs. That's actually the work that we started before my tenure. And my friend, one of the superstar I call, that in US, and he started a different system. He started, excuse me, in germanium. You see the band gap versatility is constant. He started a germanium phase, like a germanium, to make a tunnel FET, and I'm going to show you that. And unfortunately, I feel bad for him that he could not make through, because that's the much more complex problem than this gallium arsenide, indium arsenide system. So I played very nicely compared to my friend that he started that, and it's very, very, very difficult. I'm going to show you some data because it is how difficult it is. Okay, now these are the two systems here. Mixed arsenide antimonide, we work in the other faculty, other university, and that's my pre-tenure, and the germanium and InGaAs just after tenure, just to be safe side. Okay, which is difficult, most difficult, germanium InGaAs, super difficult. To show you the data, okay, that's the design. My student did that, and I'm going to skip that just to show you the device data. This is the simulation. My student did a simulation. I said that everybody talk about this germanium InGaAs. My friend is working on it. Is it good? Then student said, I don't know it is good or not. Let me simulate that. I said, okay, don't put the fuzz factor on the simulation. Make sure we can build it. We can do it. So I put another student that he's kind of watching this simulation guy, and they said that, hey, I'm going to build, or I'm going to make it, make sure your simulation parameter makes sense. Means there are two students working, one simulation, one experiment. So on the lab. And so then this student, he simulated the data looks, you see here, this work, the green color, you see that here, sub-threshold slope at 10 millivolt per decay, and this work funded by Intel. Intel is very happy, take it. So Intel asked me, can you able to make it a 40 millivolt per decay sub-threshold slope? I told him that forget it. Give me millions of dollars, maybe I can try that. Because you need lots of materials growth to figure it out the interface. And we're going to show you some of the data there. So very promising. And you see that the germanium on InGaAs, it is a tensile strain, means that the percentage you see here, the strain that you give a strain, that germanium band gap becomes direct. Means around 1.65, the germanium is a direct band gap, because that means that the gamma point, the heavy hole and light hole, they're the same line. And I have some slide band structure I'm going to show you when I talk about photonics. So that is the very cool stuff. Can you make a direct band gap germanium? It's good? Yes. What can I do? I can make a tunnel FET, and I can make it basically a laser. So this all the simulation, then my student did a memory design and circuit and all sort of stuff. The Intel found that this student is really cool. Then they took him their group. So he's in Intel working on it. So basically this is a simulation, and he did some experimental work, but not much on this, but by my other student who's working on that. So then we said that, okay, simulation good. Let's make it build a device. So this is our growth facilities. By the way, another thing to tell you, those are material expert, that we all know that germanium is the dopant of InGaAs, and arsenic is a dopant in germanium. Gallium is a dopant in germanium. Did you hear that? Means arsenic out diffuse during the germanium growth, game is over. Gallium out diffuse during the growth, done. Germanium in diffuse InGaAs, over. That interface has to be pristine, and that has to be, I should say, that should be interdiffusion, minimal interdiffusion. That has to be controlled. So how do you do it? There are many people, they say that put the germanium on the 3,5 compound semiconductor chamber, no big deal, open the shutter, you're all done. That doesn't work. So, and we have a 2 chamber, as you see here, that's a germanium chamber, and those you are right, white color, and then this is the 3,5 chamber. What does it mean? That one chamber dedicated for group 3, indium, gallium, aluminum, arsenic, antimony, that materials combination growth, and another chamber dedicated for boron, tin, germanium chamber, that dedicated for tin germanium growth. And they are interconnected, ultra high vacuum chamber, -10, we transfer the sample from 3,5 to germanium chamber, from germanium chamber to 3,5 chamber. This is good or bad? Yes, because we don't want any cross contamination between the chamber, and we try to minimize the interface. And I'm going to show you some of the data there. So this is the material stack. Please, those are material expert, and have a look here. I don't want to scare you. Until the green, the figure A, no issues. Means you ask me to grow tensile germanium on InGas, any composition you want, until say 35% we did, around 30%. 30% we did, the next goal 35%, higher strain we need. You know, the game is really start when you want to put the top layer, and Professor Partho Sao is the expert in the laser. I'm going to show you the data. You need 1.5 micron, 1.5 micron to 2 micron thick layer on the top of this thin 20 nanometer germanium. Please remember that is going beyond my screen, that thickness you need. Bottom, no issues. Top is a scary part. So you can see that how to confine the carrier, and this, the top part, that interface is the most challenging interface. That means once you grow this material, and cross doping has to be prevented, interdiffusion has to be prevented, defect has to be prevented, and smooth interface, lattice matching must be there if you grow on silicon. So these are the different strain, as you can see here, and these are the sharp interface. We need that, and we characterize those material and using our X-ray. And what you are noticing, maybe one of them I can go through that. Right hand side, 1.94%. That's called reciprocal space map. It has a X-ray unit. X-ray unit has a pixel detector. I'm pretty sure you have that. You might have a powder or thin film. And then these are the every contour represent every material. This is gallium arsenide. The middle top is the strain germanium. The bottom is the InGas. So these are the signifiers that the separation, the difference between top and bottom, to tell you the strain, the fatness, the x-axis, that will tell you that your how defective it is. The top difference, again, the top to bottom lattice difference give you how much strain or how much composition or mismatch. The sidewise, they tell you that how much defective it is. What do you want? You want very skinny reciprocal space map and narrow, you want that. Why is that? Then your defect is very less. And the left hand side on the epsilon, 0.75, 1.6, 1.9. Please remember, these are the number targeted based on my student who simulated the tunnel fed of germanium and InGas. So now we're going to characterize the material. Okay, before we do that, this particular student, my master student, he's a direct PhD. And then, you know, that we have about 90, we have 130 total faculty member, 90 tenure track, if you know that, remaining are the instructor. So my department head is the committee member, and he said that I will sign your certificate, MS degree, if and only if you show me the interdiffusion minimal. You said that interface, germanium and InGas, interface should be minimal based on the X-ray and other stuff. He said, I don't believe it. You need to show me the data. So we kind of stuck on that. Please remember that interface to be abrupt. No interdiffusion, means no germanium go here or arsenic goes here. If there goes, that has to be really minimal. Minimal means how minimal the minimal is, right? Is it a 1 nanometer, 2 nanometer, 10 nanometer, 100 nanometer? How much it is? See, this kid is stuck pretty much. So then we send sample to Intel. This is called atom probe tomography. I'm pretty sure India has it. Somebody has it. Maybe love to collaborate our samples. It's a atom probe tomography. It basically does what? During TM, you remove every atom by atom, they reconstruct the space. Please watch here. This is the in gas, germanium, red is germanium, gallium, indium, arsenide, and these are the atom they picked up, and these are the cone, like a volume, and then they construct for us the germanium situated on arsenic, and you see the Intel, this is the picture, they came from them. They said that it is a 6 angstrom interdiffusion, means 1 lattice constant interface control we can grow. That precise we can grow that between germanium and InGas. So we didn't publish yet, so then the student get a master degree, he's continuing his PhD. So that basically we did. Then we said that, I told my student that is it a fluke? Something happened. Remember, you send the samples, luckily happened, you cannot repeat it. Basically game, I call game is over. Basically you are done. So we send some more samples to Intel, and this is a very expensive measurement, and love to collaborate. Anybody has it. We have a lot of cool samples we can discuss after meeting and to do understand the interface abruptness. Good or bad is good because that's the tunnel fed that's a tunnel junction. That junction is the where the carrier can tunnel for the tunnel fed. So you understand that. Then we do a lot of microscopy, cross-section TM. As you see that in-gas on the top and germanium and this, when you publish a paper, we just, like people does not show that. Please watch here. Do you see that here? That's the strain field, tremendous strain. It make a 3D growth. You cannot make a 1.5 micron. It's a lot of tricks you need to involve. Put a sample that we send and we get that this atom probe tomography. Okay. So then ask my student, okay, this is looking good, interface looking good. How about the defect into the germanium? If the germanium, I'm going to make a photonics or something, how much the defects? Where? Here, in this layer. How much it is? So this is the master student. As soon as he did a good work, he left to Georgia Tech because we lose a lot of good students to the top school. So at least I lose 2 students there. So then he came up. He's a very, very amazing kid. He's cleverly, just please watch the slide here. This one, what he did, he make a plan view. What I'm noticing here, plan view TM, you are top down, you are looking into the defects. Means this is the stack, what you are noticing, the bottom picture, that where the in-gas is in here, you put your eyes, go down, and moving your eyes from your right to the left, where the 3.5 degree angle there. Do you see that here? So basically, as you are moving your eyes, what you are noticing, you are counting the defects where really the defect is. And you see these lines on the plan view TM, the misspeed, these are the misspeed dislocation line, and they abruptly stop at this. And you see the red dotted line, those are basically the different images he took and he put together for the TM. And this we didn't publish yet, we're going to send that, and that basically telling us that the germanium, the strain germanium, the 30 nanometer, as you see on the left hand side, is very hard to see misspeed dislocation. Does it mean that it is zero defect? No, there's nothing called zero defect. There are some defects that we may not be able to see it. What my student said that the defect you see is the upper bound, but the defect should be less. I asked him, why do you think? He said that think about a paper. Once the germanium is very thin, that is called plastic relaxation. It's like a bending it. It's like a bending. Think about a paper, you can flip it. Once you bend it, you can generate some plastic or additional defects that when that layer is so thin. So then he come up these kind of a cool ideas that do that all the materials tricks to get the quantify or qualify the material for the device. Then we measured the band offset. As you remember, the EB effective unit Intel 1.1.2. So we do a lot of band offset by XPS, X-ray photoelectron spectroscopy, to do the germanium InGaAs. So this is basically to feed back this data to my model student that who did the modeling. So this is the experimental data feed to the modeling. So that is good. So then mean that basically we did a lot of circuit and other stuff. We did that. And what we couldn't do it is the tunnel fed, real tunnel fed working. That because we don't have a E-beam lithography. And tunnel diode long device doesn't work. You need about 20, 30, 40, 50 nanometer device dimensions we need. And we don't have that in our school. So we are kind of struggling every day. So to make that devices, we have a stack, we have grown the stack, we characterize, you saw here, but we could make the real tangible device that I can go to Intel that, hey, here it is, the device is there. Because, and then question that why Intel cannot fabricate? Yes, they might have the data, they won't tell us because it's a diode current flow one way. You give the information to them, they will never tell you how good your material is. They will tell you, okay, we got it, that's all. So we don't know that yet. So that basically my students is not graduating yet. He's going to demonstrate some tunnel FET, but that difficulties you are facing it. So that's my student here. So next, my other student did to show you. I'm not going. He wrote a review article. I told you that this is fabricated by another school. My collaborator did that for us, and we grow the stack, and they did for us. But you know, the device development is so expensive and so time consuming that they cannot help us. So I asked my student, we again materials group, and that my student said that this is the student, and can I tell you how this kid is. I'm very fortunate to have a student like this kind of student. 13 journal paper within 3 years, 25 journal paper. I wrote 12, he wrote 13 to get his degree, 25 journal paper to get a PhD degree. And 3 years, less than 3 years he was here. That productive this kid is. I'm very fortunate, this student. So I asked this kid that, hey, this stack, this material stack, the layer structure is good at this. But Intel told that once you increase or once you make a device and you heat it up 100 degree, they told me that your game is over because all interface will destroy. You cannot have a working device. So how can we help being a materials group? So me and my students sit down and we said that, can we do a X-ray measurement, in situ X-ray measurement? Please remember, you put the device stack on the X-ray machine, you collect the data, room temperature, you will keep hitting it, collecting, keep hitting it, collecting. This kid was present, I believe, 36 hours to collect this data. Please watch that here. He increasing this temperature, stabilize, measure X-ray. There is no material issues. So I asked my student, yeah, this is good, but do you think Intel will believe it? They said that why can't we send this device to a group, independently verified? They can measure the device at different temperature, same thing, same duration, remeasure it and tell us how good it is. So that's he wrote a paper of TDMR. So that kind of a complex that the material analyze this kind of a data. So you can see it. So I ask my sometimes student, right? Hey, did you have the same data that you accidentally plot 25 degree, accidentally something happened. He came and told me, Dr. Hudait, it doesn't. I said, how do I believe you? He said, look at that contour, left-hand side A and right-hand side, this reciprocal space map, 25 degree. If you clearly see that, the contours are different. I said, yeah, I trust you, but I know that carefully analyze the materials for the device. And so going with I hope I'll give you some feedback with the material challenges, and we optimize the interface, we characterize the defects, we do the band alignment to make this tunnel fed device. So now I'm going to move to the FinFET, and if you and give you that. When I was Intel, I have a 1, 2, 3, 4 patent of the same title, extremely high mobility CMOS logic. Please check the year. Intel still couldn't demonstrate anything. Intel, forget about university, a small group, and 2-3 students and little funding, the Intel. So this is the idea. And then IBM and with applied materials, please check the slide. Those are working applied materials or something. And they come up that is, please here, 3.5 and germanium. I put the date for you, July 2014. And this is the devices. So when I see the picture and student came and told me, Dr. Hudait, look at that, this picture, so cool. I said, okay, hang on. Can you able to do this orientation? This orientation, the FinFET has a 2 orientation, 100 and 110. The 110 side wall and 100. First, do that. Tell me that the material is good before you go and fabricate the FinFET. You know that we don't have E-beam lithography. We cannot make a. N is the node. 22 is the 22 nanometer, 14 nanometer, 7 nanometer, 5 nanometer, 3 nanometer. Please remember, 5 nanometer, 3 nanometer nanowire FET. Your prior speaker was talking about nanowire based devices. You know how difficult to grow on that? A 5 nanometer, 3 nanometer, that's the fin to make it, the pillar to make it, and billions of those. We don't know that, how difficult it is, but I told my student, make this orientation first. So we did that. And then, interesting, and so I asked my students, suppose, what I generally do, my group is very small, like a 4 PhD student, 1 master's. I club 1 experiment guy student and 1 theory student put together, so that one can give a feedback. Theory knows that what experimental can be achievable, what the experimental student knows, what theory, what did he put, what fast factor did he do, is not possible. Okay. So the kid, he was 5 years old when I left. He's my advisor's son, youngest son, 5 years. When I left him, India, 2000, he was 5 years old. So he came to our group. Sir told me, Mantu, take my student, take my son and do whatever you want. I said, what does it mean? Now graduate him and do something. So he came to my group and I asked him to simulate this. He's just graduated now. And he came from Bangalore, some private school. So what the message here? So I asked him, if the germanium my student going to do and the InGaAs, is it good? Is it Intel? We're going to go and tell Intel, hey, this is good. So my student said, okay, I can simulate. So this is the calibration data, not our device data. This is the line is the simulated. The circle data is the Intel FinFET data. So my student established the model first, make sure the model is working, make sure he can benchmark everything. Then he predict a 10 nanometer FinFET, and the data looks very promising. So we told Intel that if you guys can fabricate your FinFET until 10 nanometer, I think this is really cool. So he did a lot of things, not the one slide I just presented here. He did a fin width, fin height, aspect ratio, all sort of stuff he did that. Again, my expertise, not this circuit simulation, device simulation, materials. I told my student, can you able to make it? Can you able to make a materials? Can you show me a materials is good interface materials? So put another student on that. So now, so I took a volunteer to my student to help. I said that let me grow the germanium on silicon. No good, don't do it. I told my student, don't do it. So one student did it. She graduated, she left to Georgia Tech. I said that, why can't you grow the germanium on gallium arsenide? Please remember, lattice matching. Grow gallium arsenide on aluminum arsenide, that also lattice matching. Please remember, lattice match to lattice match to lattice match, but mismatch to silicon. What we care, the device part should be lattice match. That should be far away from silicon. That means the defect should far away from silicon. So that basically the stack I designed. I asked my student to grow it, and I wrote a paper. I'll show you the materials. And that's the stack that my student did. He left to Georgia Tech for the TM. This is the gallium arsenide grown on silicon. Aluminum arsenide, I can tell you why it is aluminum arsenide. We put germanium on the top. That is basically the fin. Will be the fin. You know the GOI, the people talk about SOI wafer, the silicon on oxide on silicon, or germanium on oxide on silicon, and think about that. The oxide is the large band gap. That means the top layer have a isolated by the oxide layer from the bottom layer. It's like a sandwich, it's completely separated out, that part. So that aluminum arsenide acts as a blocking barrier, acts as your insulator. And you can see the interface, how control we can do. And this material stack, my student did electrical data and all the other stuff. He's now at Intel. So I asked my student, okay, this is good. I cannot give you a degree that because your advisor involved here, you need to tell me that interface is 6 angstrom again. Because earlier you showed me 6 angstrom, you need to show me also 6 angstrom. Otherwise, I want to sign your master degree. So student basically stuck again. So then the student said, okay, Intel, again, Babe Intel. Then we send the samples to Intel. So please watch what you're noticing here. The red is germanium. The blue is aluminum arsenide. The green is gallium arsenide. This is the stack here. And this is the same stack. Please watch germanium, aluminum arsenide, and gallium arsenide. That's a boron doping. That's a different purpose we put. And then that stack is identical of germanium, aluminum arsenide on gas. And Intel measure. And please watch the abruptness here. So we are ready for then. And 6 angstrom abruptness, they told us this is the person. And we are so happy, so proud that yes, we can grow a 6 angstrom resolution of the material, both mismatch and lattice match. So they would not do any measurement. They said that, Mantu, your sample is so good. So why do you need again and again measurement for us? But we have many other samples. We have a team germanium. We grow many stack. We grow. Anybody can help for any collaboration. We are always happy to collaborate on that. So, and then do a lot of oxide work we do for the transistor. And this is the paper I wrote that. And this is a student who my group. And I told him to stay in the US. He left to Hyderabad campus, and he did work and he frustrated there, sometimes the funding or research. Then he told me, please help me, I'm going to leave India. Then he's in IMEC now, he's doing excellent work. So this is the kid who helped me here. He was a postdoc in our group and came from IIT Kharagpur. IIT Kharagpur PhD, radio physics student, radio physics MSc, IIT PhD, IIT Kharagpur PhD, postdoc, my group. And then he went back to Hyderabad. I told him not to go. And then he's in IMEC right now. He's doing cool. So this is the kid that he deposited all the oxide work for us. And my other student did that here. So you can see that how pristine interface or oxide we can deposit on the germanium. Why 110? As you know, 110 is the thin sidewall. So we care most. Then, so I asked my student, okay, everything is good. This is a new student came in on the board, and please see the stack here. This is a tunnel fed stack. Yes. Germanium on in gas. Yes. I told him that, Rudbik, can you make this, the germanium as a P and in gas as the N? He said, you asking me to do 10 nanometer FinFET? I said, no, even 100 nanometer we can do it. Just forget it. Do a simulation and tell me that this is good. Alternate CMOS, and it is better than ITRS roadmap. Means the current FinFET is the aspect ratio, fin height to width ratio, please remember height to width ratio is about 4.5. He told me, say 4. And I told him that, can you do aspect ratio 1:1, means 1 height to width ratio, and show me that circuit good. Again, I'm not a circuit person, but this is a materials guy. But he did that so that I can put another student to work on the material. So he did that, and he told me that he did all the detailed work and inverter design he did, and he told me that 20%, look at that here, 20% to 25%, that gives the best performance for the delay, matching delay for N in gas and P germanium. That means this side in gas and germanium. Please watch here, N channel FET and P channel FET, and he told me that this will be really cool. So I told him to do ring oscillator and other stuff. So he's working on it. And hopefully we are trying to reach out to Intel, excuse me, to fabricate the FinFET if they can. Of course, they won't tell us the device data, but at least we'll be very happy that if they can fabricate the alternate channel CMOS. So we can give them a feedback for the material side and the circuit side. So that basically my student did that. With that, taking the lot of materials and idea and growth, so I'm going to show you a few slides about the photonics, that how difficult it is. Right here, everybody use a laser, the bonding and the communication and other thing, right? Professor again, Partha, the expert on that. We are not, we just a materials group and taking this idea and put together a stack, and you'll see how difficult it is. And so we told me that we can make a germanium direct band gap. You need a direct band gap no matter what, and you want to make sure that you control the defects, and you should able to have a cavity. And we got some funding last year from Ireland, Northern Ireland, and US to demonstrate that. So this is the band structure diagram that we did. Please watch that in the class we teach. The L side, the gamma, the L side, the band minima is lower than gamma. Please watch here. What you're noticing, germanium on 3% in gas. Consider this is pure gallium arsenide and your L is lower. So you need to make the gamma down. So by straining that, the pink color, please watch, pink represent this, green is here, they need to flip. So, and they flip, but the difficult part, even if you make it a direct, but still your density of states is still lower than your L. So we need to make sure that you need to have enough doping in the conduction band so that the ledging action can happen. So we did a simulation. This is the first principle calculations done by Ireland group, and we work together. And again, we are materials group. So I told my student, demonstrate that. Please grow it. Please grow this stack and then these layer structures. So we going to show you. This is the structure here. I think again, Professor Sao asked me, how could you confine your optically? I said, yeah, that's excellent questions. And please watch here. This is the stack. How much and germanium laser? We grow 13 nanometer, and we need a 1.5 on the top, 1.5 on the bottom. Minimum we need. That basically a cartoon that you can confine here. Again, I think I articulate to you that the quantum well to the bottom, no issues. We can do it. The game start, the top part. Top part is the most critical part, where the things that you need to really careful to design that part. And I'm going to show you the next slide there. So question is that, can I ask my student to grow and demonstrate this stack? And then I told him that, yeah, I will not give you a degree. That's not fair for the kid. So I told him that, can you dissect this problem? Dissect means you make it a step by step. You grow quantum well like a thin, just germanium on the bottom, then thin layer on the bottom, then top layer on the bottom. Like a piece by piece, you puzzle put together. Then my student did that, and we can show you here, germanium on indium aluminum arsenide on gas. This is just no cavity, no top layer. This is the part, germanium on the bottom, no top. So he did that. He analyzed the data. Then I told him that I need some cavity that my friend asked me a long time back. My student said, okay, doctor, with that we can grow it, no problem. They grow, and this is the cavity they put on the top, and 16%. So I told my student, this is 16%. I want direct band gap. Please watch here. That direct band gap, if I back for a 2 slide, how much I need here? 24%. Please go back to the lab and grow 24% and give me the material with the thick layer on the top. So then again, in the student need to understand that, characterize it, right? So then they went back. Then this is the laser structure, 13 nanometer. And this is the modeling did by the Ireland group. And we grow the stack. I'm going to show you the next slide, how difficult it is. And look, very interesting, very promising. if we can make it and control the defects at the top interface. And this is just funded, this work. And I wrote a paper last year sitting, and this with the design and the metals growth. And now I'm going to show you a next slide. See the defects here? Can you see here? Misfit dislocation line. Can you see 3 dotted line and through blue line? These are the misfit dislocation of the interface. So I told my student, yeah, this is good. You just cherry pick some area which is looking good. I want enter stack. Please show me enter stack. So then they analyze the data, and here the stack here, and you see that interface, bottom interface, no issues. You may not be able to see that because your germanium is 13 nanometer. So, and the top layer is 2 micron. The TM scale, you cannot allow you to see. So we blow it up, and that basically the top interface, that's the bottom interface, and the detailed work. If you want to see the all sort of microscopic analysis, all details, it is published, just available in my website, PDF copy, and also the journal office. So that basically, and that right here, and you can see here that my student blow up picture, they show me, and that's the distance line. And please notice that getting this kind of TM image, it takes a year to wait, almost a year to wait to get a data, to get it done. It's super difficult. When the old student get a job, 130, 140K job after PhD, when the new student come here, they have no time to waste here to teach because they have money is waiting, 130K is waiting there. So that basically transferring knowledge from one student to other student, we always suffer, always difficult, always we face because there is a very small group. So that's sort of delaying a lot of work on that to demonstrate that. And then we measure the luminescence, ask my student, yeah, this is looking good, but I need a photoluminescence. I just want to make sure it is the laser, the light coming out, at least by photoluminescence. We didn't fabricate the device yet. Why we didn't fabricate that? We have to have a better quality material on the top to fabricate the device. This is like a fast material ever grown and analyze, understanding. So that basically the phase we are right now. And then this is the Tyndall Ireland. They did a photoluminescence, and we see that there's a cavity, no cavity, cavity, no cavity, cavity. Means the top layer, it has no top layer, no top layer. So this measurement also and the modeling they did kind of figuring out there where the crossover happening. Is it a 1.5%? If you read the literature, somebody saying 1.5, somebody saying 1, somebody saying 2. We have no clue on it where it is. If I say 2, my student cannot graduate because 2 means very hard to get a good quality material. So I asked him that let's other person, third party validate our material to do that. So we basically did that here. So the goal to fabricate the devices and for this from the laser. And our facilities and my student, we have some modeling capability. We have a Centaurus TCAD. We have a Crosslight to do optical modeling. This is our growth. And after I joined, we purchased the X-ray. It has a pixel detector. It's a triple axis detector. The cool stuff is that I requested department to help me to buy a temperature X-ray stage. Means this X-ray stage, as you are noticing, the sample mount here, the stage we can increase to 1000 degrees C. Of course, we won't go that, but we use up to 600 in situ. We put the samples, we stay there, we measure, increase, measure, increase. This is the solar simulator in our lab. This is our access. This is our shared facilities, clean room. This is growth, this is X-ray, this is the FM shared facilities. This is my lab. We do mobility. If you need any help, low temperature, we can help you on that. Optical microscope, Intel donated to me. I have a very fancy probe station to do the transport. I didn't show you here. IV, CV, temperature dependent IV, DIT calculations, all sort of fanciness. This is the one. The beauty of that, it can go low temperature, liquid helium capability, but we don't use liquid helium, too expensive. Liquid nitrogen to 200 degrees C. Why 200 degrees C? Because Intel told that any device, non-silicon device, you need to at least to show us the IV measurement 150 degrees C. So that's why we went to 100, 200 degrees C. The stage can handle on that. Then what we did cool stuff, we also mount, the solar simulated solar light on the top of this window. Means we can shine the light also during the measurement, light induced measurement also we can do that. And that another capability, we have a high temperature. It can go to 300 degrees C, my lab. That's the measurement setup, semiconductor parameter analyzer, solar simulator facilities. And then these are the shared facilities. Don't use it, just to showing you that we have a capability. They will not allow my student to use it, and they use the other TM system. And these are the basically the SEM and SIMS and SIMS. We don't use. We give a samples. We pay them money, $100 per hour. They charge. They do the measurement. They do the measurement, $100 per hour, $200 per hour, $100 per hour. There is another TM machine my student use. And then this is the outreach. Sometimes we do. Some students come here, showcase the lab. And this is the brightest girls. Every year in the summer, there are 50 students come to Virginia Tech. They are junior, senior, means they're 11th grade, 12th grade. If you get a chance in this program, your admission guaranteed. Means they give this kid a offer letter that you have admission in this our school. They're that talented. And so me here and next to me, this is my daughter. My daughter didn't select my school because of dad here, and she selected UC Berkeley, and she's graduating this year. And this is my student showcasing some of the stuff here. And so with the summary, I'm going to show you that the defect and interface control is the most challenging because the defects can reduce the career lifetime. We didn't show you the data. We are writing a lot of paper and for the lifetime, and very hard to measure those. Defense lab helping us as a free germanium in-gas CMOS. We are simulating it. We have a stack. Would you help us? Would you fabricate for us? We can send you the stack to you. So we can collaborate that. And tunable laser, we're going to fabricate. That's the project we got. And lattice matching device structure on silicon. Maybe one day we can put together on photonics and electronics and silicon. Then that will be really cool. This is maybe I need to graduate maybe another 10 PhD students to do this. But here we are now. And thank you for that. And if we can do, if we all can do, all together, some piece of it, then I believe that we have a societal impact is tremendous. You have a photonics we can make, we have an IoT space we can help. We see that the implantable devices, the low power that we are talking about, germanium in gas. If you fabricate, you like to fabricate, we can give you the materials. And low power electronics that Intel has that. And I'm going to show you the slide that when I left Intel sent me this picture to me. They said, Mantu, you'll be very proud. I said, why? He said that you see that Intel going to bring a new material right here, Samsung new materials, all sort of stuff that we kind of share with that. And I'll stop here. Any questions that you have, and I can answer to your questions.
Thank you, Dr. Hudait. It was quite an interesting talk.
Thank you.
So the listeners, participants, you can put up your questions.
If you have any questions or you feel that you don't have a time, or sometimes the student kind of scared to ask questions. I know in the class, in the seminar, the advisor sitting there, you have my email ID. Feel free, and I should say, please send email your questions. If I can answer, I will put that question to my student. They are Indian student. They must need to respect the questions and address to your concern.
So maybe we'll have some immediate questions. Yes,
please.
Yeah.
I have one question.
Dr. Goswami, yeah.
I have one question.
Please.
Interesting, very interesting talk, because we would like to have a photonics electrons together, probably.
Yes.
And we are using German as a photonics part, and silicon gallium arsenide as a electrons part. Okay. So as I have seen that a lot of fabrication we have done in this direction, But how to make the germanium? Of course, you are telling that lattice is mashed and it's make a super lattice probably. How to control all these things? 0.28 indium, which machine is used?
So we can walk through you very briefly. Thank you for these interesting questions right here, maybe here. So basically, that people that will not tell you the growth tricks. You see the graded composition. We grade that material. We start with the indium very small with aluminum arsenide. We slowly grade the material to control the defects within the material. Then we grow the germanium layer. The germanium is there are separate chamber. So if you put that germanium on the compound semiconductor, maybe briefly I can show you the reactor. I know my postdoc advisor will tell me that I can do it, but I will tell with respect, sir, you cannot, because you cannot put the germanium on 3,5 chamber because germanium is the dopant. So what we is right here. So right here. So Partho, you see here, I'll show you the chamber. See the linearly grade. We do the grade. Once we finish the top this composition, we cool down the material to about 150 degrees C. Make sure no thermal cracking. Then we pull it out from the growth chamber. Then we transfer to the vacuum chamber to the germanium chamber. Means if I go back to my reactor, then show you the right here. So we grow up here, cool down, take it out. See the rod, see the magnet, the blue, the red color magnet. These are the magnet basically. Please
are you taking up manually?
Manually, everything manually. We don't do robot, and I can tell you that I'm here at Virginia 12 years. None of my students allowed to transfer sample from chamber to chamber. I only do, because it's very tricky. If you can drop the sample, the student will cry. So after the growth, please take here. We'll take that, we place germanium chamber, we grow, take it back again, place the 3,5 chamber, then we complete the growth. So give you an hour to stay in the lab. 16 hours we stay in the lab to complete the laser growth. 16 hours. 1/6. We stay here in the lab. Even the advisor stay here.
The critical fabrication.
Yeah, so we don't, okay. The problem for us, the device, the last part we stuck. The last part we all stuck. Because we don't have e-beam lithography, we all stuck. And so that basically our problem is. We understand the material, the interface, the defect engineering, the X-ray, the material, the interface. Then circuit simulation, student doing it. But how about a 20 nanometer transistor? We cannot do it here.
Okay. Good.
Yeah, nice. Some more questions? Anyone?
Please.
Yes, sir.
Yeah, Dr. Goswami.
Yes, sir. So, sir, actually we are. Yeah, sir. This is Rupam here.
Yeah, Rupam, go ahead, Rupam.
Yeah, sir. So we are basically working on the theoretical part for tunnel field effect transistors. Basically, we have not yet moved into the 3.5 thing. And one of the challenges that we face here is the interface traps actually mimic the experimental part in the simulations. So can you throw some light on that particular part? How to consider the interface traps basically?
Yes. So I'll go back to the picture here. And Rupam, I will send you two paper to you. And you don't have to read the entire paper. I'll tell you the figure number. Just glance those two figure number, and I can tell you that.
Sure.
Let me here. And here.
Yes, sir.
Here. So do you which tunnel pair are you simulating it in general, or this stack, the gallium arsenide, antimonide, indium gallium arsenide, or germanium in gas? Which one you are simulating it?
Sir, in general. Sir, we are basically
Which material
currently
stack?
on the
Or in
homojunction
general?
part on silicon. Only silicon homojunction tunnel FET.
Tunnel FET, but which material combination? Is it a gallium arsenide, antimonide in gas stack? The picture, the slide you see here?
No, sir. No, sir. No, sir. It is a silicon-based.
Silicon-based. Okay,
body.
perfect. Got it. Okay,
It's a silicon-based body.
That's no issues. Okay, so that when we did this work and we found that the defect at the interface, what you like, right? That EV effective drastically reduce as your defect at the interface.
Yes,
so
yes,
what you'll do, you make a coding or programming that EV effective as a function of your defects at the interface.
Okay.
And what we did, this is the work done by Penn State. They did the modeling and we did the experiment and we calculate the EV effective and we told them this is the EV effective you put in your program and get the defect number. This is other way, opposite we did. We told them EV effective as a function of defect. They went back, then they put that number to mimicking our EV effective. So you modulate EV effective as a function of defects.
Okay, sir. Okay.
Did it clear to you? Clear?
Yeah,
because
thank
that's
you.
your
Thank you,
tunnel.
sir. Thank you
That's
so
your
much.
the tunnel
Yeah.
barrier, because that's the most critical part on it.
Yeah. Yes. Getting the abrupt and a defect-free interface is the greatest challenge that we face in designing a tunneling barrier.
Yes, that's absolutely correct. Because we did that, and Rupam, if you feel that you can, you saw our presentation, right? And material stack
Yes,
right
sir.
here, germanium
Yes,
in
sir.
gas. We did simulation circuit. My student did his and that interface is pristine. You saw that TM image, and
Yes.
that we stopped. We gave up. Gave up means just forget it. Why? Very hard to control it. And the
Yes, sir.
arsenide antimonide. So we have that because when we learn the tunnel fed germanium in gas, that learning we translate to the photonics. That learning we translate to the CMOS.
Yes, sir.
So again, to tell you that maybe that if you okay, I'm just sorry, I'm not taking your time here. I'm going to show you very quick here.
No, sir. No, absolutely not. Yeah.
Why can't why I mean I'm just it is a thinking, right? Since my students simulating it, maybe if you can help, we can jointly write a paper that this stack like right here. See that here?
Yes, sir.
My student
Yes, sir.
simulating
Yes,
he
sir.
already did. He already completed. He's writing an IEEE journal. This is the
Yes, sir.
EFET. That's the NFET. Make a alternate channel CMOS. Since you have
Yes,
a
sir.
simulation experience, and
Yeah.
why maybe think about that, we can feed you some data if you need. And this is my student simulated. This is the one snap he gave me that, but this is the CMOS circuit simulator. This is inverter. He doing ring oscillator. He going to do something else.
Okay, sir. Yes,
So
sure,
your
sir.
answer to your question is EV effective.
Yes, sir. Sir, I'll email you on regarding this. I would love to work on this.
Sure.
Yeah. Thank you, sir.
Sure.
Thank you so much.
Sure. Thank you. Yeah.
Okay, so if there's no more immediate questions, maybe the students can ask their doubts later on through email to Dr. Hudait.
Sure. I mean, if the student feel also not to send email to me, they can send email to the advisor, you all, and then you can just forward those email to us. We love to answer any questions you have there, because that's the way it is. What happened that, who knows that I have a 2-3 proposal pending. Who knows that I might need a student in the next year or next spring or something. Some student might be a good fit our group.
Yes. So thank you, Dr. Hudait, for the wonderful talk. And
thank you for inviting.
Yeah, thank you for your time, and thank you for joining us.
Sure.
So,
thank you. Take care, all. Stay
Thank you.
safe. Okay, sure. Bye.
Thank you, sir. Same.
Bye. Good night.
Good night.
Thank you, sir.
Thank you, ma'am.
Thank you. Partho, I'm calling you.
Yeah. Copy. Thank you.
Okay, Dr. Goswami, over to you.
Yes, sir. I thank you, Professor Vijay Kumar Nath, for carrying out the session today, and I take this opportunity to thank all the participants who took out their time and joined this 5-day series. And this is the second time that we have organized this after we had seen the interest another 1-day webinar series. So therefore, this time we extended it to a 5-day series with different areas. And I also thank all the speakers who really were very grateful, and they agreed to deliver their valuable talks at this 5-day webinar series, starting from Shri Harpreet Singh Jatana sir from SCL ISRO up till today, Mantu Hudait. And all the sessions, I hope, have helped the students and the participants, and of course the faculty members who have been an integral part of this 5-day series. And I this opportunity again to thank every one of you, and we hope to future so that it spreads out to the world outside. So thank you everyone, and I have shared the link to the attendance cum feedback form in the chat box, and I request you to fill it up. And regarding the e-certificates, we will take a 15-day window to share with you the links to the certificates. So please be patient, because we'll have to go through the official signatures from the conveners and then preparing the certificates. So thank you everyone. I thank each and all of you present here. So with this, we come to the end of this webinar series, and thank you. Stay safe.
Thank you, sir.
Thank you, sir.